Question number 1. So let's concentrate on the small packets first, which have 5 envelopes in each of them. So if we had one small packet, given there's 5 envelopes in each, that'd be 5 envelopes. If we had 2 small packets, we would have 10 envelopes. 2 times 5 is 10, and so on. If we had 3 small packets, given there are 5 envelopes in each, we would have 15 envelopes. So what is the relationship between the number of small packets and the envelopes? Well, we just times it by 5. So if we've got x small packets, then we have 5x worth of envelopes. Same with the large packets, where we've got 20 in a large packet. 1 packet we'd have 20 envelopes, 2 packets we'd have 40, and so on. So y packets, y large packets, we'd have 20 y's worth of envelopes. So the total number of envelopes we have is 5x plus 20y. T represents the total number of envelopes, so T equals 5x plus 20y. Question 2. So a question where we have to construct an equation and then solve it. So let's start constructing an equation to show this. So we're told that Ali has X cards. So Ali has X cards. Now Belinda has twice as many cards as Ali. So it doesn't matter how many cards that Ali has, Belinda has 2 times as many. So if Ali had 10, Belinda would have 20, and so on. So how do we work out how many Belinda's got? We double whatever Ali's got. So we double x, which is 2x. Now with Charlie, we're told he has 5 more cards than Ali. So make sure you read the question carefully. It's 5 more than Ali. Well, Ali has x, so however many Charlie has is just x plus another 5. So x plus 5. Now we're told they have a total of 33 cards between the 3 of them, between Ali, Belinda and Charlie. So these 3 together must add up to 33. So x plus 2x plus x plus 5 has to equal 33. So we've constructed an equation. Now let's simplify the left hand side. X plus 2x plus x is 4x plus the 5. So 4x plus 5 equals 33, which is what we had to show. Now for part B, this is what we're more familiar with. This is just solving the equation. So we start off by subtracting 5 from both sides, giving us 4x equals 28. We then divide both sides by 4, giving us x equaling 7. And x is the number of cards that Ali has. Ali has x cards, so our final answer is x, which is 7. Question 3. So 5f take away f is 4f, 4f and 2f is 6f. Now for part B, when we're simplifying this, there isn't a huge amount we can do. 2 lots of 8 is 16, then it's 16 times m times n, which we write as 16mn. Now for part C, t squared plus t squared, well we've got something and then we just add another one of these, so we've got 2 lots of t squared, so that's simply 2t squared. Be careful, this does not say t squared multiplied by t squared, which would have been t times t times t times t, which would have been t to the power of 4. So be very clear in your mind the difference between when you're adding terms and when you're multiplying terms. Now part D, given that y equals 4x minus 3, work out the value of x when y is 13. So just start off by rewriting the equation, but y equaling 13. So 13 equals 4x minus 3. And now we just have to solve this. So we add 3 to both sides. So 16 equals 4x. We then divide both sides by 4. So x equals 4. Now for part E, the only catch is to make sure we follow BIDMAS. So with this first term, remember to do the squaring, because it is indices, before you do the multiplying by 5. All right, the powers, the indices, are done before the multiplication. So it has to be 2 squared, which is 4, and then 4 times 5 equals 20. So it's 20 take away 7, which is 13. Question 4. So expanding gets rid of the brackets, and then the simplifying is when we gather like terms. So let's start off with the expanding. So we have a claw and a claw. So 5 times p is 5p, 5 times plus 3 is plus 15, minus 2 times 1 is minus 2, and be careful with this one, minus 2 times minus 2p is plus 4p. So we've expanded, we now do the simplifying, so we gather up our p's, 5p plus 4p is 9p, then we gather up our normal numbers, 15 take away 2 is plus 13. Question 5. So to simplify this, we just have to gather like terms. So gather up the x's and gather up the y's. 3x plus x is 4x, and 5y plus 4y is plus 9y. Question 6. So gathering up our m's, 1, 2, 3, 4, 5 m's, so that's 5m. Part B, 2p plus 7p is just 9p. And then when we simplify this, there's really not too much we can do apart from just set it out losing the time signs, because we don't need the time signs. It's just assumed when we have 4tw that means 4 times t times w. So we put the number at the beginning, so you must do that, and then by convention it's nice to put the letters in alphabetical order. So 4 times t times w is 4tw. Question 7. So triangle A is reflected in the x-axis to give triangle B. So this red line here is the x-axis, and then we reflect triangle A over this. So it's just the mirror image. So for example, this point here is 1 square away, so remains 1 square away. This point here, for example, is 1, 2, 3, 4 from the mirror line. So going backwards, 1, 2, 3, 4. So B is a reflection of A. Well, we're then told that triangle B is reflected in the line x equals 1 to give triangle C. Now be very careful. This vertical line down through 1 is x equaling 1. Okay? Picture all the coordinates of the points that form this line. For example, 1, 1, 1, 2, 1, 3, 1, 4. The x coordinate is consistently being 1. So this line here is x equaling 1. Avoid assuming any of the x equal lines are parallel to the x-axis. They are not. So anyway, once you've got your mirror line in, the reflection is fairly straightforward. We've just got to reflect B over the mirror line to become C. So for example, this point here is 2 from the mirror line, 2 from the mirror line. This point here, for example, 4 from the mirror line, 4 from the mirror line. Now this final part is quite a common question where you can summarize a couple of reflections as being a rotation by 180 degrees, with the center of rotation being where the two mirror line cross. So the red line crosses the purple line at the coordinate 1, 0. So rotation by 180 degrees about the point 1, 0. Now remember, when the rotation is 180 degrees, you don't need to specify whether it's clockwise or anti-clockwise, because it doesn't matter which way you turn. If you turn round halfway, you're facing the opposite direction, whether you've gone clockwise or anti-clockwise. Question 8. So I think we can just see that this is a rotation by 90 degrees. If you just picture it and just imagine this swiveling around by 90 degrees, that this point here is going to be behind this point here, so here and so on. The tricky bit is working out where the center of rotation is. So really I think the only way to do that is to have your tracing paper draw around the shape and just experiment around this area, and you will see that it is 1, 1. I mean, you could kind of picture it if you take this point here and just picture going down here and up here. That looks like it's forming a right angle, which will be your 90 degrees turn. But really, it's just trial and error around the sensible, obvious points where it could be. Question 9. So this is just a reflection in the y-axis. You can see that it's just reflected over, and all the points are the same distance away from the mirror line on either side of the reflection. Now part B, just following the instruction, so we're told the centre of rotation is 0, 2, so mark this on the diagram. Get out your tracing paper, pop the tracing paper over shape A and the centre of rotation, and a little tip, to draw a little arrow pointing upwards on your tracing paper, then push the point of the pencil in on the centre of rotation using it as a pivot, and rotate the tracing paper 90 degrees clockwise so that your arrow is now going to be pointing to the right, and you will see that the shape has moved to down here. So press firmly through the tracing paper to leave an indentation on the paper below, and then just remove the tracing paper and draw over this indentation, and then just double check. Just go and repeat the exercise and make sure that indeed this is the final answer. Question 10. So describe fully the single transformation that maps P onto Q. So P onto Q. So we can see it's the same shape but bigger. So the first mark will be for saying it's an enlargement. Just take any length of your choice. For example, the length at the top. This has gone from a length of 1 to a length of 3. So our second mark is for saying the scale factor 3. So the lengths are 3 times as big. Now to get the centre of enlargement, just draw a couple of these sunshine rays through similar points. So for example, the bottom right hand corner is here and here. So get out your ruler and draw a construction line through that all the way back, filling the graph paper. Then take another similar point, for example top right and top right, draw another sunshine ray through there, and now where these sunshine rays cross is the centre of enlargement. So the centre of enlargement here is 0, 0. I could have taken any of the similar points. All of the sunshine rays will go through the centre of enlargement. Question 11, so very similar to question 10. We can see we've got an enlargement going from A onto B. It's just a bigger version of the smaller shape. The scale factor on this occasion is 2. If you take the base, for example, it's gone from a length of 2 to 4, so it's twice as big. And popping in my sunshine rays, I can see my centre of enlargement is the coordinate 6 minus 5. Question 12. Well, I can see if I put the mirror line in of the x-axis, this is just a reflection of one onto the other. For example, this point is 1 away from the mirror line. This point here is 2 away from the mirror line. So 1 mark for saying it's a reflection, and the second mark for saying the mirror line is the x-axis. Question 13. So here I can see shape B is just shape A having been shifted 4 to the right and 3 down. So just to make sure you count the squares correctly, take a similar point, for example the bottom left hand corner, and just focus on that point moving. So I can see that's gone 1, 2, 3, 4 to the right and 1, 2, 3 down. Now to illustrate 4 to the right and 3 down, we use a vector where the top number represents the left or right. So as I've gone to the right, that is a +4. The bottom number in the vector represents the up or down, and as I've gone down, that is a -3. Now when we shift a shape, it's called a translation. So just remember that word. It's a strange word to use, and don't muddle up translation with transformation. Transformation is any of the shape movements. So a transformation may be a translation, rotation, reflection, or enlargement. So the translation is one specific transformation. A translation is when the shape is shifted. So 1 mark for the word translation, 1 mark for the vector 4 minus 3. Question 14. So we can see this is another shift. P is just shifting 6 to the right and 1 down. Again, just to make sure, take a point common to both. So for example, the top right hand corner, and focus on that point. So this point here has gone 1, 2, 3, 4, 5, 6 to the right and 1 down. So that's a translation by the vector 6 minus 1. Question 15. Now this is a pretty tricky question. So just take your time, and if you don't fully understand this, it's not the end of the world. This is going to be one of the harder questions on the paper. So we're told that these are mathematically similar shapes. So the white trapezium is just a small version of the bigger trapezium in which it sits. Now, in order to sort of relate the two shapes together, to see how much bigger one shape is than the other, you look at the question and you see where you are given the same information for the two shapes. Now, with this one, you can see that both of the shapes were given the top length. So we can see that on the small trapezium, the top is 12 along, and on the bigger trapezium, the top is 18 along. So the relationship is 12 to 18. Now I can simplify that. I can divide both by 6, so I can see that my relationship is 2 to 3, or in other words, the big one is 1.5 times as big as the smaller one. 1.5 lots of 2 is 3. I could have worked that out of my calculator by doing 3 divided by 2 if it's not obvious to you. So basically all the lengths on the bigger rectangle are 1.5 times bigger than the lengths on the smaller trapezium. I think I said rectangle or triangle then. I meant trapezium. Okay, all the lengths on the bigger trapezium are 1.5 times bigger than on the smaller trapezium. So for example, length AB, which is the left hand side of the bigger trapezium, is going to be 1.5 times as big as the left hand side of the smaller trapezium. So AB is going to be 5 times 1.5, which is 7.5. Now part B is particularly difficult. Okay, now if the length relationship is 2 to 3, which we've established up here, then the area relationship is going to be the square of these. So the area relationship, area being two-dimensional, is 2 squared to 3 squared, which is 4 to 9. So if the area of the smaller shape is 4, the area of the bigger shape would be 9. This is the relationship. Now we're told that the trapezium AEFG, which is the smaller trapezium, has an area of 36. So the smaller trapezium has an area of 36. Now 36 is 9 times as much as our ratio. So if this is 9 times as big, so much this one be. So if the area of the smaller trapezium is 36, the area of the bigger trapezium is 81. The relationship 36 to 81 is in the same proportion as 4 to 9. It's just that each of them is 9 times as big. Now, the area of the bigger trapezium is 81. The area of the smaller trapezium is 36. So the area of the shaded region, which is the big trapezium, take away the small trapezium, is 81 take away 36, which is 45. Question 16. So for part A, 2 of these shapes are congruent. Now congruent means it's exactly the same size. So just imagine that you cut all these shapes out and then you could pick them up and turn them around or turn them upside down or whatever. Which of these shapes would fit on top of each other? Well, A would fit on top of G. So A and G are congruent. Now shape H is an enlargement of one of the other shapes. So here's shape H. So we're just looking for a smaller shape which is proportional to this. Now if you look at F, you can see it's the same shape, just smaller. But all the lengths are half as big. The base of the rocket, if you like, is 1 and not 2. And then the side of the rocket, if you like, is 1.5 rather than 3. So H is an enlargement of shape F. So question 17 is very similar to question 16. The triangles C and D are congruent. If you cut C out, it would go and fit on top of D. One of the triangles is an enlargement of triangle A. Well, we can see that's triangle F. It's just a bigger version of A. And the scale factor, you've just got to see how much bigger each side is. So for example, this side here has gone from 1 to 2, so it's twice as big, so the scale factor is 2. Question 18. Now I think with these I very much prefer the approach of just thinking about the proportions rather than relying on that speed, distance, time triangle. So let's think about what's going on here. We're going from London to Sheffield, and we're told it took him 3 hours at an average speed of 80 kilometers per hour. Now, if Gary's going at 80 kilometers every hour, it's going to take him 3 hours to go 240 kilometers. 3 times as long, he'll go 3 times as far. So for Gary, it's going to take him 3 hours to go the 200. He's going to go the 240 kilometers in 3 hours. Now we're told that Lynn drove from London to Sheffield. She took 5 hours, assuming that she drove along the same roads and did not take a break. Work out Lynn's average speed. Well, from a calculation we did for Gary, we know the distance from London to Sheffield is 240 kilometres. It's taking her 5 hours, so 240 kilometres would take her 5 hours. Now, to work out the kilometres per hour speed, we need to see how far she would go in 1 hour. So we need to divide this by 5. To go from 5 hours to 1 hour, we have to divide by 5. So if it's a fifth of the time, it's going to be a fifth of the distance travelled. 240 divided by 5 is 48 kilometres per hour. Now, if Lynn did not drive along the same road as Gary, explain how this could affect your answer to part A. Well, obviously, if she's going along different roads, it could take her a longer or it could be a longer or a shorter route. Her speed could be different, the time taken could be different. If Lynn did not drive along the same roads again, explain how this could affect your answer to part A. So she could be travelling a longer or a shorter route, or in other words, she could take her a longer or a shorter time. Question 19. So a sprinter runs 200 metres in 25 seconds. So we've got to work out the average speed of the printer in meters per second. So we need to know how many meters they go every second. So if they go 200 meters in 25 seconds, how far would they go in 1 second? Well, this is a 25th of the time, so they're going to go a 25th of the distance. 200 but divided by 25 gives us 8 meters per second. Question 20. So Emily drives 186 miles in 3 hours. So what is her average speed? Now, her average speed is how far she goes on average every 1 hour. So we need to think about how far would she travel in 1 hour. Well, 1 hour is a third of the time. So she's going to go a third of the distance. So we're going to do 186 divided by 3, which is giving her an average speed of 62 miles in 1 hour, 62 miles per hour. Now, Sarah drives at an average speed of 58 miles per hour for 4 hours. How many miles does Sarah drive? Well, remember, 58 miles per hour means she travels 58 miles every 1 hour. So if she's got 4 hours of travelling at this speed, she's got 4 times the time, so she's going to go 4 times as far. So 4 lots of 58, which is 232 miles. Question 21. So, who has the faster average speed, Debbie or Ian? Now, we're told that Ian drives at an average speed of 66 kilometers per hour. So we need to work out how fast Debbie's going on average, and then compare this to Ian's 66. So looking at Debbie's distance time graph, and I've just taken this reading for example, I can see that she goes 20 kilometers every 16 minutes. I've just taken this reading here. I could have taken any reading I wanted, but that's just the one I've taken. Okay, perhaps 25 kilometers in 20 minutes might have been a more sensible reading. Anyway, that's the one I've taken. So if I've gone 20 kilometers in 16 minutes, how far will I have gone in 1 minute? Well, I've just divided by 16, because this is 16th of the time, so I will travel a 16th of the distance. That means I'm travelling 1¼ kilometers every minute. So in an hour, which is 60 minutes, I'm going to be travelling 60 times as far. 60 lots of 1.25 gives me 75 kilometres. Okay. Again, say I'd taken 25 distance in 20 minutes, I'd have just times that by 3, again giving me 75 kilometres in 60 minutes. So Debbie's travelling at 75 kilometres per hour, Ian's travelling at 66 kilometres per hour, so Debbie has the highest average speed. Question 22. So the sign says 30 miles in 26 minutes. So how many miles would we go in 1 minute? Well, let's just divide both of these by 26, because you've got a 26th of the time. 1 minute is a 26th of 26 minutes. So if it's the 26th of the time, we're going to go 26th of the distance. So 30 divided by 26 gives me 1.153 ... miles per minute. Now if I multiply this by 60, so 1.153 ... times 60, I can see that I go 69.23 ... miles in 60 minutes, so 69.23 ... miles in 1 hour. Now the speed limit is 70 miles per hour, so I'm just keeping underneath the speed limit. So when Lethna says we will have to drive faster than the speed limit, she is not right, as 69.23 miles per hour is just less than the 70 miles per hour speed limit. Question 23. So let's set out a diagram to gather all the information. So we're going from Liverpool to Manchester to Sheffield, and we're told it's 56 kilometres from Liverpool to Manchester, and then 61 kilometres from Manchester to Sheffield. And then we're also told Ollie's average speed from Liverpool to Manchester was 70 kilometres per hour. So Liverpool to Manchester, he's going 70 kilometres per hour. That's 70 kilometres in 60 minutes. So 70 kilometres in 60 minutes, if we divide that by 10, for example, that means we go 7 kilometres every 6 minutes. Now I've got to go 56 kilometres, that's 8 lots of 7. So if I multiply both of these by 8, I see that I go 56 kilometres in 48 minutes. So it's taking Ollie 48 minutes to get from Liverpool to Manchester. 48 minutes. Now the question tells us it took him a further 75 minutes to drive from Manchester to Sheffield. So in total, the time it's taken him to go from Liverpool to Sheffield is the 48 minutes it took him to go from Liverpool to Manchester, and then the 75 minutes from Manchester to Sheffield. That's a total of 123 minutes. Now the total distance he's got to go is the 56 and 61, which is 117 kilometres. So his average speed is 117 kilometres in 123 minutes, which is 0.951 ... kilometres every minute. Now, how many kilometres would he go every hour? Well, it's 60 times as long, so he'd go 60 times as far. So you multiply this 0.951 ... by 60, giving us 57.07 ... kilometres every hour. So an average speed of 57.07, or 57 kilometres per hour to the nearest kilometre. The question didn't specify how accurate, so I've just gone to the nearest kilometre. Now for part B, this is a classic question where it says Janie's average speed from Barnsley to Leeds was 80 kilometres per hour. Our average speed from Leeds to York was 60 kilometres per hour. And they say that you can work out the mean of these by just adding the two and halving this. Now that's only going to work if the time taken for both parts of the journey was the same. Only going to work if the time taken for both parts of the journey is the same. Question 24. So this is Jane's distance time graph. So we're told this is her walking to the ice rink, stopping at her friend's house on the way. So this is her walking to her friend's house. This little bit here is when she's staying at her friend's house. This part here is her walking to the ice rink. This is her time at the ice rink, and this is her journey home. So part A, how long did Jane stay at her friend's house? Well, that's from 2 o'clock to 2:30, so that's 30 minutes. How far is it from her friend's house to the ice rink? Well, this is how far her friend's house is from Jane's home. This is how far the ice rink is from Jane's home. So the distance from Jane's home to the ice rink is 7 take away 3, which is 4 kilometres. Now what time did Jane leave the ice rink? Well, that's here. That's halfway between 5 and 6, so that's at 5:30 p.m. I should have said p.m. there, 5:30 p.m. Question 25. So Simon went for a cycle ride. He left home at 2 o'clock. The travel graph represents part of Simon's cycle ride. So clearly he cycled for a bit, had a rest, cycled for a bit, had another rest, and then cycled home. So at 3 p.m. Simon stopped for a rest. How long did he stop? How many minutes did he rest? Well, we can see that's between 3 and halfway between 3 and 4. So that's half an hour, 30 minutes. How many minutes did he rest? 30 minutes. Part B, how far was Simon from home at 5 p.m.? Well, at 5 p.m., which is here, we go up and we see how far he was from his home, and that was, he was 20 kilometres from home. So 20 kilometres from home. So 5 p.m., go up, take a reading, 20 kilometres. Now, at 5 p.m., Simon stopped for 30 minutes. So, okay, so we just, he remains 20 kilometres from home for 30 minutes. So I've just filled in that part of the graph. It's just flat from 5 o'clock to 5:30. Then he cycled steadily at home. It took him 1 hour 30 minutes to get home. So anyway, he started cycling home at 5:30. So if it takes him 1 hour and 30 minutes, he gets home at 7. So we've just got to do a straight line because he's going at an average speed from 5:30 all the way until 7 p.m. Question 26. So this was a tricky question, and I don't think you would get anything as difficult in this because I'm not sure we've covered in second form changing between kilometres and miles. But no harm learning it now, and really what you've got to learn is that 8 kilometres equals 5 miles. Okay, 8 kilometres is 5 miles, so that's the key proportion to learn. So once you've got this on board, this question's fine. So Martin also cycles to work. On Tuesday, his average speed was 16 kilometres per hour. So he goes 16 kilometres every hour. Now 16 kilometres will be 10 miles, so Martin actually goes 10 miles per hour. Now, who was the greatest speed, Lisa or Martin? So let's go and work out Lisa's speed from her distance time graph. So just take a reading. I've taken this reading here. So I've seen that Lisa goes 4.6 miles in 30 minutes. Now, to get a speed, I need to know how fast she would go in an hour. So if I double both of these, I see she goes 9.2 miles in 60 minutes. She goes 9.2 miles per hour. So her speed is 9.2 miles per hour. Martin's speed was 10 miles per hour. So Martin has the greater average speed. Question 27. So Ria left home at 1 o'clock. That's fine. She drove for 30 minutes at a constant speed of 40 miles per hour. So let's think about it. She went 40 miles in 40 miles per hour means she would have gone 40 miles in 60 minutes. But she drove for 30 minutes, so she drove for half the time, so will have gone half the distance. So she's actually gone 20 miles in this half an hour. So we can see that this represents 20 on our distance time graph. So we can see that every 4 squares represents 20. So another 4 squares means that there would be 80. So that's the first thing. She then stopped for a break. Well, we can see that we've now established this was half an hour. So we know every 2 squares represents half an hour. So she had a break until 2 o'clock. She then drove to the hospital at a constant speed. Yes, we can see her doing that. So given that is 1, 2, 3, 4 squares along, and 4 squares represents an hour, we can see she got to hospital at 3 o'clock, at 1500 hours. Now, she was at the hospital for 30 minutes. So just completing that part of the distance time graph, another 2 squares, another 30 minutes. She remains at hospital. She remains 40 kilometers away. Now, we're then told she drives home at a constant speed of 32 miles per hour. show that she does not arrive home before 4:30. Now we've worked out that she is 40 miles from home when she's at hospital, and we've worked out that she leaves hospital at 15:30. Now if she was going to get home by 16:30, that would mean she'd have to travel 40 miles in 1 hour. She would have to be going at 40 miles to get home by 4:30, but we're told that she drives at a speed of 32 miles per hour, so clearly given that she's going at 32 miles per hour and she would have to be travelling at 40 miles per hour, we can see that she does not arrive home before 4:30.